Answer the question, how do you write a good multi-electron wave function? We're going to start out with the ground state. We'll move on to excited states later, but let's start with the ground state of the helium atom. So the helium atom has a nucleus with a +2 charge on it, right? Z equals 2 there. And then we've got 2 electrons we have to worry about. Electron 1 at a distance R1 away from the nucleus, and then at a distance R2 away, we've got the second electron. Now, if that's all we had, to be an easy problem, it'd be just like the hydrogen atom. We could easily solve that, but we also have to worry about an electron-electron repulsion. Now, as always, we're going to solve this problem by write down the Schrödinger equation. We need to define the Hamiltonian. There's going to be a kinetic energy term, a potential energy term, but then we're also going to have to worry about this electron-electron repulsion. And if we were being really good, we would also add in a spin-orbit term, right? That came from the Dirac equation. That goes as z to the 4th. So in a low Z atom like helium, we won't have to worry about that. So let's just forget spin-orbit coupling, but we will have to worry about these other 3 terms. Let's define those in a moment. And then we're going to find the wave functions. That's really what we're going to be interested in today. And of course, the final part would be to go back, take these wave functions, substitute into the Schrödinger equation, and find the associated energies. All right. Today, let's concentrate now on defining the Hamiltonian and writing these wave functions in the right way. Okay, so our Hamiltonian, as I said, is composed of kinetic energy term, potential energy term, and then this electron-electron repulsion term as well. For the kinetic energy and potential energy, right, minus h bar squared over 2 mu, put the reduced mass in there, and then there's a second derivative with respect to the coordinates of electron 1, a second derivative with respect to the coordinates of electron 2, right? And then we have to worry about the electrostatic interaction of the electron, -1, with the nucleus +2 charge, right? So that's going to be, get the units right, e squared over 4 pi epsilon naught, and that's z2 over the distance to electron 1 plus 2 over the distance to electron 2. All right, good. Without this term, we'd have independent electrons. Well, think about that some more. E, right? That is going to be equal to, again, you got your e squared over 4 pi epsilon naught to get your units right, and then the distance between the electrons, 1 over r, 1, 2. Right. In the hydrogen atom, didn't have that. We know what the answers were, the regular sp,d orbitals. We know still the angular part is the same, right? And that's going to be the case here, that we're going to have orbitals for each electron that are based on the spatial coordinates, right? As well as we're going to have to worry about the spin coordinates. But there's an angular part, and then, or the angular part and a radial part, right? And then to get it all completely correct, we also have to multiply by the spin part. We have to tell which m sub s value we have. And of course, all electrons always have spin equals 1, but their spin can be either up or down, plus or minus m sub s, plus or minus 1. Right? We're going to apply the central field approximation. Right? That says that each one of these electrons is in its own orbital, moving in its own space essentially, and so we're going to make a complete atom wave function. Right? Each one of these electrons is moving in the potential of the nucleus and the other electrons in the system, and we'll make an atom overall wave function that's going to be a product of the individual ones. In this case, we have 2 electrons, so we'd have a psi 1 times a psi 2. Now that certainly ought to work for the spatial part. Let's concentrate on that, but we know we're going to have to come back to deal with spin at some point, right? So let's think about that ground state of the hydrogen, or the helium atom. The ground state of the helium atom, right, has a 1s squared electron configuration. 2 electrons, each one of them in an s orbital. Right? So that means principal quantum number 1, 1s, right? Magnetic quantum number L, or the angular momentum, orbital angular momentum of 0, and the magnetic number is 0 as well. The difference is going to be in the 2 spins, which have to be paired. All right, but we know that much. So if we take that central field approximation, each electron are occupying a spin orbit, right? One is phi1, one is phi2, right? What would be the probability of finding electron 1? Well, it's the square of the wave function, right? So the probability of finding electron 1 at a position R1, right, would just be equal to the absolute square of this phi1 at that position. Similarly, the probability of finding electron 2 at position R2 would just be the square of its wave function. What about the probability of finding both electrons? 1 electron at R1 and 1 electron at R2. The probability of finding electron 1 at R1 and finding electron 2 at R2 simultaneously would just be the product of these 2. Okay, so that motivates us as well. It says, yeah, this makes sense that we can make a wave function for the atom out of a product of individual spin orbitals. Okay. May have to worry about how that interacts with the Hamiltonian later, but it certainly describes the probability density properly, or so it seems. What else do we have to worry about? Okay, so now we're going to make this spatial part of the wave function. So let's call this the spatial part, because eventually the whole atom is going to have a spatial and a spin part. So the spatial part of the wave function looks like the product of 2 spatial wave functions, one describing the probability distribution of each one. Okay. Or if we really wanted to write it in terms of the quantum numbers, then we could write this spatial wave function as psi 1, 0, 0 for electron 1 and psi 1, 0, 0 for electron 2. What else do we know about electrons? Electrons are indistinguishable. And that means if we swap, we don't know which one is electron 1 and which one's electron 2. So the mathematics have to show this, that if we swap R1 and R2, we should get the same spatial distribution. So if we square the wave function, we should get the same result, right? That seems like a no-brainer, all right? Electrons are indistinguishable, so the distribution doesn't matter whether we call one electron 1 or one electron 2 or the other way around. The distribution has to be the same. However, and very important rule of quantum mechanics, just from the structure of quantum mechanics, is a good multi-electron wave function must be antisymmetric with respect to electron interchange. Oh, so while the distribution does not change on interchange of electrons, when we take the total wave function and we interchange, which one comes first, which one comes second, it has to be antisymmetric. That is, there's a sign change. That's what we mean by antisymmetric. Okay, so if we interchange the identity of the two electrons, the sign of the wave function changes. This is related to the Pauli exclusion principle, right? The Pauli exclusion principle says no two electrons can occupy the same spin orbital, or more appropriately stated, more to this rule, no antisymmetric wave function describing an n-electron atom can be made up of one electron functions, two of which have the same set of one electron quantum numbers, right? No two electrons in the atom are allowed to have the same quantum numbers. If they have all the same spatial quantum numbers, their spin quantum number has to be different. On m sub s up, on m sub s down. Okay. So now let's take a look at what the implication of that is for the overall wave function.